And I would like to invite now Chryssa Kouveliotou from George Washington University to talk about the Swift Girls Observatory Deep Galactic Plane Survey, goal, design, and first results.
Hi, I'm Chryssa Kouveliotou from George Washington University, formerly at NASA, back in the academia, trying to work both in research and in teaching. I have actually worked very closely with Neil at the time even of the SWIFT proposal. At that time, we were competing because when I was at Marshall, we submitted a proposal called IBEX. And we were competing directly with SWIFT. SWIFT got it, and the next thing that Neil did was pick up the phone and asking people who were not in this proposal to work with him in the SWIFT team. That's the kind of person Neil was. A very gentle and very inclusive person, trying to get the best opportunities for his team, for his group, and for the science overall. Last spring, actually, in the fall of 2016, Neil called me and said, we need to organize another SWIFT conference in Santorini, Greece. I set up doing this. I worked with him and I worked with the local organizing committee. His health progressively deteriorated. We moved it away from Santorini. We made it in DC because it would have been an easier place to be. And sometime in February, I got a call from Ellen Williams, Neil's wife, saying, you know, we may end up having a memorial meeting. And that's what we're going to have in DC in May 21st, 22. In 2018, we are organizing in the National Academy of Sciences the Neil Girls Memorial Meeting. You're all welcome to it, and we're going to announce the program very soon, I hope. I've worked, as I said, with Neil in many projects that encompassed a narrow scientific area, but we were all fellow travelers in these quests. We were all wondering what the enduring quests are in our field. Neil was one of the very few members of the field that was part in all of these. He was certainly addressing one of the main and ever-present questions of how does the universe work, how we probe the origin and destiny of our universe. He was also working on how did we get here, explore the origin and evolution of galaxies, stars, and the planets. And as you just heard from Brad, are we alone? SWIFT was actually, even before this project that's now starting on exoplanets, Neil was talking about trying to also look for exoplanets and see how we can make SWIFT work on exoplanets. So he was kind of a universal scientist, not as narrow as most of us in our field are. I worked with him on several projects. This particular one is a project that I actually came up with and tried to make sure that we were able to do it, namely, how can we use the unique capabilities of the X-ray telescope on SWIFT to observe and survey our galactic plane, our own galaxy, because SWIFT has surveyed many nearby galaxies, but there aren't many deep, homogeneous, uniform observations consistently monitoring our own galactic plane. So I tried several proposals with Chandra. They said it's a very ambitious program and it may be done down the road. I discussed this with Neil, and Neil said we'll observe it with Swift. So I submitted a proposal, it was accepted, and my student Nick Gorgon is now actually working on it full time. We're having a blast with it, and he even spent some time to create a logo. So this is the Deep Galactic Plane Survey logo, courtesy of Nicholas Gorgon at George Washington University. I will discuss here 3 projects that we worked with Neil. One of them is the Galactic Plane Survey, and that's present. The other 2 are in the future. Problem is I have. So how did I come up with it? A long time ago, I wanted to actually do this, but my determination kind of solidified when I ran across this particular picture. This is the result of the work of a young kid, well, when he did it probably was a kid, who worked with his brother and his father, taking photographs, literally photographing our galactic plane. He went 100,000 miles all over the Earth and set up cameras because he wanted to take a complete image of our galactic plane and put together all these images into a collage that would show what the galactic plane looks. This is the combination of about 37,500 photographs. And of course, he has other areas that basically are even more resolved. But this is the whole galactic plane. And I'm pretty sure he enjoyed working for at least 6 years putting it together. If someone can spend 6 years to do this just because not even being an astronomer, we as astronomers have the obligation to do the best we can to make a similar survey in different wavelengths because we have the capability and we know how to work on it. So we started it, and here is why we're doing this. It has never been done in the depth we're doing it. Simultaneously, we have, besides the XRT, also the UVOD data as a bonus. We see that at the same time. We have observations in the X-rays. We also have observations in the UV. We will have the capability to enhance the transient populations in the Milky Way. We'll see a lot of X-ray bursters, and we actually have already, be it low mass or high mass. We hope to enhance the population of magnetars, of which we have about 28 only in our galactic plane and 2 in the clouds, Magellanic clouds. We will see, and we do see, flaring stars, CVs, and there is an open discovery space there. Anything can come up. And of course, we complement the Sunplane survey, which is using Chandra data, serendipitously observed to collect information, as we will see. Team members, I won't go through all of them, but you probably will recognize that there is NuSTAR, ZTF, there is people who work on flare stars, there is theorists, there is the SWIFT team, there is again the NuSTAR team, there is part of NICER and part of MAXI, and we're growing because we will add people. Anyone here who would like to join, please let me know, because we're finding things that we do not know how to interpret on how to put them in a general context. Remember, we're X-ray and gamma-ray astronomers. We're finding CVs and we're finding flaring stars. We need people who have worked on flaring stars to make sense out of it. So we need you if you know how to do that. What's the difference from the earlier surveys? So the earlier X-ray surveys, and I have not included here the BAT survey because it's higher energies, has been mostly all-sky surveys and that was done with ASCA between 0.7 and 10 kV, but with 3 arc-minute resolution. With ROSA, it was rather shallow, 0.1 to 2.4 kV with 5 arc-seconds resolution. And there was the galactic plane survey for parts of the galactic plane of integral above 17 kV with 12 arc-minute resolution. So what we're doing here is the XRT galactic plane survey between 0.3 and 10 kV with 5 arc-seconds resolution. The initial survey, obviously we could not ask for the whole plane in one go because it would probably block SWIFT for at least a year and continuously. It was about 4.4 million seconds. So we went for a first part with 40 degrees, 40 square degrees, which are in 2 regions where the scutum and the Perseus arms encounter the bar, the galactic bar, which is plus or minus 10 to 30 degrees in longitude and plus or minus half a degree in latitude. So basically it's 1 degree in latitude for 40 degrees. It's basically 40 square degrees. The total, and I will show you an image very soon, is 366 overlapping tiles. Each 5 kilosecond total exposure for a total time of 1.8 megaseconds, which we are splitting in 2 years because we still want to have other science done with SWIFT and not just the galactic plane survey. The survey is going to be complete up to luminosities 10 to the 34 ergs per second, up to the end of the galaxy beyond the galactic center, and about 10 to the 33 up to the galactic center. We are not just using the observations that we have with SWIFT. We are going to use archival data, serendipitous archival data, and there is a ton of it. And also we will use follow-up observations with other satellites to be able to probe and identify the nature of these transients. So here is a simulation of our galaxy. And from the sun, we're observing, we're monitoring, we're surveying these 2 swaths here. And the reason is because most of the sources that we're going to look for are concentrated. So we actually started with the area where we know we're going to find many sources. We hope we are correct. If you go to magnetars, now unfortunately this is turned upside down, so the sun is here right now. A lot of the magnetars are concentrated. These are the 2 swaths that I mentioned before. A lot of the magnetars are concentrated in these 2 areas. So we're hunting where we know there is enough prey. Hopefully we will be able, if this works as we hope it will, to extend, and since SWIFT is going to be up for at least 5 or 6 or 10 more years, we're hoping to complete the whole galactic plane. Another very important population is the galactic high mass X-ray binaries. This is results from integral. The sun is back where it used to be in the first slide. And what you see here are the dots of the integral sources of high mass X-ray binary nature, which basically have been observed. There's 53 of them. They're not all here, I don't think. But the bottom line is there are areas where you do not have enough, you have not been probed enough. So we hope to be able to go farther and complete as much as possible the population of both magnetars and high mass X-ray binaries. In fact, if you plot the location of the known sources in the 2 areas that we're surveying, these areas have 40% of the galactic magnetars and about 30% of the high mass X-ray binaries. So we hopefully have a good chance to get more of these sources and complete as much as possible their population. Obviously, we're not going just for the hope. We have planned very carefully all the tiles. Now the tiles, so each circle is the field of view of the X-ray telescope, about 20 arc minutes in radius. And basically, I'm sorry, it's 20 arc minutes in diameter. And basically, we have made sure that they overlap so that we have a reference point by about 4 arc minutes. And they are entangled together, overlap together. So here you can see it better. So there is areas where there is 3 of them together. And in these areas, sometimes where there is overlap, we were able to identify new sources that were not in the single tile, because obviously you have 3 times the exposure there. So we're gaining a lot by putting everything together and completing the map, as well as by finding new sources. What you see here, all the black circles are the SWIFT XRT field of view. But all the other colors you see are all the archival data that exist already in these fields. And you can see that there are areas that there has been no observation whatsoever. And obviously, you understand that this has a lot of observations because there are other sources there. If we expand to the rest of the plane, we will have less and less and less overlapping data. The light cyan is XRT observations. The red are Chandra, and the pink and purple are XMM observations. So we have access, and we are adding these observations to every single one source that we think is worth following up. So there is a lot of work here. It's probably work for more than just one graduate student, but right now we're just starting slow, and we will continue. Obviously, we didn't, as I said, leave it up for a hope. We did a pilot study. So we did take 9. Here you only see 8. There's 1 tile missing here. The first thing we did, we observed for 45 kiloseconds, 5 kiloseconds each, 9 tiles, to see what are we going to find before we start in a mission of 1.8 megaseconds. This area was selected. We went into the infrared data, and I selected a place which had some infrared data which would help us identify previously existing sources, and nothing which would show whether we could find new sources. So this area had minimal prior coverage in X-rays, relatively good infrared coverage. We found 7 sources. Of the known, 3 of them were known, and 4 of them were brand new. Of the known sources, 1 was a magnetar, 1 was a supernova remnant, you can see it here, and 1 was a high mass X-ray binary. Interestingly, when we looked at the actual previous information for each one of the 3 sources, we found out that the current detection of the supernova was increased by a factor of about 16, 15.6 times in flux than the previous measurement by Chandra, which is something we are going to follow. And right now we can, because we have a Chandra Target of Opportunity program, accept it, but when we first did this, we did not. The other thing we did is we calculated, based on this pilot study, how many transients do we expect in the survey? And we concluded that we are expecting something between 150 to 200 transients per year. So remember that number. One of the most difficult problems that every survey has is making a concrete identification of the sources that you find. You see an X-ray source that is about 3 sigma above the background. It has 50 counts. What is it? What else can you do with 50 counts? So what we're doing here is we're estimating the hardness of these sources. The first thing we do is trying to identify where most of the photons are emitted, in the soft range or in the hard range. So Nick is keeping 3 catalogs, sources predominantly in the soft area, sources predominantly in the hard area, and sources that are all over the place. They have a uniform spectrum. Then in George Washington University, we have a group already that has developed a source identification pipeline because they were doing some similar work in very high energy cosmic ray sources, HESS sources, and their identification with X-rays. And this is the name of MUW class. They already have, and they're using machine learning. This is based on machine learning. And they're having already a data set of about 8,000 identified sources to actually compare to. And it uses data in multiple wavelengths: infrared, Spitzer, glimpse, MIPSCAL, and WISE. Near infrared, 2MASS, UKIDS, and VISTA. Optical data, radio data, and UV data. This is already underway, and we have now a pipeline that is connecting to this pipeline, and basically every source we're finding goes through the whole thing and comes up with a whole page for the source telling us what catalogs have been searched, what has been identified already that exists in this location, and the name of the source. At the same time, we've been busy writing proposals for follow-up observations, and we now have accepted proposals for 5 targets with Chandra, another 5 targets with XMM Newton. The Newster PI, Fiona Harrison, has actually agreed to declare this also a legacy program for Newster, so all the, as is for SWIFT. So all the targets that will be observed and followed up are going to be done by the Newster mission as well. We started collaborating with NICER. Peter Bilt is our closest collaboration, and I will show you the results of this. And we are starting to collaborate with ISS MAXI, which has been proven very fruitful. We also have a program for magnetars with HST, and Ralph Vyers, who is a member of this proposal, leads the transient team of LOFAR, the low frequency array, and we're starting to, we're going to follow up with LOFAR as well. So there is a lot of resources, and I will show you where all of them came together in very, very soon. Where are we now? The survey began on March 17, 2017, that is. So far, we have analyzed 166 tiles out of the 361 tiles, out of the 366 tiles, totaling about 800 kiloseconds. We have identified 190 sources above 3 sigma, which is, in 1 year, very close to our prediction of 150 to 200 sources. These are found either the soft band, which is 0.3 to 3 kV, the hard band, 2 to 10 kV, or the full band. We find 40 new sources which have no X-ray or multi-wavelength counterparts. Among the known brightest sources, which are above 1.1 counts per second, there are 9 high-mass X-ray binaries, 7 magnetars, 3 low-mass X-ray binaries, 2 supernova remnants, multiple flaring stars. We have a lot of them, and we have interesting flaring stars, including a solar analog which I was told by one of our collaborators that it's not very easy to find, a type G25. So this is actually so this is number 2. The first one was a supernova that became brighter, and this is a solar analog, which probably I will follow because I'm very intrigued by what can we learn, if anything, from it. I have here some of our results. They're not to the level of a paper yet, but these are where we're going to go very soon. So RCW103 is a very interesting area with a lot of very active sources. There's 3 of them. We identified 3 when we observed through the survey. And we saw that the central source is actually a well-known source, and it started flaring, and therefore there were a lot of XRT observations on top of it, including these new sources here. Sorry, these sources as well. The image you see is a combination of 200,000 seconds of archival data. And this is the light curve across the time, 54,500 to 57,500 days, if I remember, if I can see correctly here. And this is how these sources evolved, all 3 of them, in this particular interval. 2 things I need to stress here. One is the red source is the central source. It could be a magnetar. This is what is being touted right now. And it did outburst at a certain time, which increased, obviously, the number of observations, and you can see is the number of points. It's been published to death. The blue source is also it's also known. It's a pulsar. The third source is where we're interested in. This source was there in the field from the beginning, but was not observed until very close to our observation, which is here, which actually is the best detection. And if you go backwards, there is nothing. So this is obviously a transient. And this is another source we're going to follow. It's an interesting place. Pulsar, magnetar, and the third source. There's a lot of interesting sources congregating in that area. This is a flaring binary that really tricked us quite a lot. At the beginning, we observed with the Swift Galactic Plane Survey tile, and we found a bright source. Obviously, we looked in our catalogs, and we found that Chandra had observed the source in 2006 and in 2016. Obviously, to get better signal, we added the data originally, and we found a very wide, broad source with 2 lobes, which puzzled us because we hadn't found one like this before. We asked our colleagues. They all thought it was a very interesting source. We were excited, but we couldn't figure it out. And then we decided to go separately, and we realized when we analyzed the data separately that these 2 sources were far apart from each other. The obvious conclusion was that has to be something with a large proper motion. And indeed, it was identified based on the fact that it was a proper motion. HD 171999, it's a spectroscopic binary, which is very nearby, 36 parsec. And it has a K star, metal-rich star, and an unknown companion. It has an orbital period of 21 days and an eccentricity of 0.05. And when we went into these data, because here it's rather faint, here it seemed to have an outburst, a flare. And the next observation with Swift at 3 kiloseconds did not detect the source. And we went to the back and found out also that there was a detection, there were upper limits there, there was a very strong detection with a flare here, and the detection later in our data. So this is a flaring star. Now, I'm not an expert on flaring stars. If anybody here is interested as an expert on flaring stars, you're very welcome to come and talk to me, and we can start finding out how to work on this data. The third example that we're actually working on right now, and we're writing a paper, is MAXI 1621 minus 501. Now, you can see here, the only reason this table is here is to make good on my previous slide how many resources we can and have poured to identifying this particular source. The detection, the discovery as a transient, happened on October 19 with MAXI. Immediately, Swift observed and detected the source as well. So it was detected with MAXI at 57 millicrop, which corresponds in the Swift area 2.7 times 10 to the minus 9 ergs per second per centimeter square. We went back in our galactic tile, in our survey tile, which had happened some time ago in May 2017, and we actually realized it was not detected. There was a limit of less than 2 times 10 to the minus 13, a very strong limit for the source. So that was a new transient. Immediately after, we found out that NICER actually had observed it. We didn't know that. We found that later. Gemini was observed to find out if there is a counterpart. And on October 26, we also observed, and we actually observed with NuSTAR. We observed again, the source went behind the sun. We observed with ATCA, and we found nothing. There was no counterpart, which really puzzled us because we were thinking at that time it was a high mass X-ray binary. And then we observed in December 2nd and 3rd again with NuSTAR when the source came back, or the sun obliged and left the area of the source. And integral observed. And we are now observing, well, actually we observed on February 22nd, just almost the day before I left, with Chandra and NICER at the same time. So what is this source? Here is the MAXI detection. This is the MAXI light curve. MAXI monitors all sources, so they went back and they found out that it was below the transient level. It raised a flag when it got at this point, and it actually has varied. This is the whole range in blue, and then it has a different range in the soft and in the hard X-rays. So it was detected with MAXI, and we have spectra from NICER, we have spectra from NuSTAR, and we have spectra from NICER, NuSTAR, and XRT. So the original spectra were indicating a disk plus black body with reflection. So we were thinking it's a black hole with an accretion disk. So we actually had 2 models, a power law and an accretion disk with reflection, and we also had an iron line as well. So we were completely certain at that point it's a black hole with a reflection, with an accretion disk. And the temperature of the inner disk varied between 4 and 2, and the flux actually increased between the 2 observations. We looked for periodicity. We have a first evidence of about 113 second quasi-periodicity, which I'm not officially reporting here because it's one of these 3 sigma detections which you wish you never had because you don't know what to do with them. At any rate, we have now better data, and we will look at them with Chandra. Then we went into the, we observed the source with NuSTAR again in December, and completely serendipitously, we detected 2 bursts. Classical type 1 X-ray bursts. Duration 30 to 35 seconds, black body spectrum with temperature of 1.9 keV. So this source now is classified as an X-ray burster, most likely a low mass X-ray binary. And even more impressively, there was a photospheric radius expansion measured with integral, which actually led to a distance measurement of 8.4 plus or minus 2 kiloparsec. So it was worth it. This is the actual profiles of the 2 moduli on NuSTAR, the orange and the blue, and this is the profile, blown up profile of the 2 bursts. So this is the first time, and probably, I hope I'm not going to say that and believe it, the only time that we had such a success all over. From putting everything we had on it, starting from 0 and knowing exactly now what the source is. And we're all very happy, and especially Nick, because he's writing it up. On February 22nd, we observed, as I mentioned, with Chandra HRC-I, and we detected 8,400 counts from the source. We have a lot of information. We're analyzing this information, and we will see whether we will proceed with XMM or other instruments. We also have Gemini data to find out what the counterpart is now that we have the location in very high accuracy. So this is the status of this project. And I believe I have how much more? 5 minutes. Yeah. Okay. Okay.
5 days.
I can, you know. Okay, so I will be, luckily the previous speaker talked a lot about what I was about to say as well for the merging, the binary neutron-star merger. So I'm going to talk about the program, a project that Neil and I were very fond of, because this is what started as a free flyer, and we were trying to put together a mission that was going to identify electromagnetic counterparts of gravitational waves, and that is the International Space Station Transient Astrophysics Observer. And there is this probe, the Transient Astrophysics Probe, of which I am not a member, but Jordan Camp, who is the PI, as he is also on this one, asked if I could present it. I will unfortunately do what I don't usually do, jump some slides so that we, in the interest of time. Okay, so here we go. Obviously, everybody has seen this multiple times. We are going to exploit the ability of the LIGO, advanced LIGO in Livingston and Hanford and Virgo together to identify for us triggers that then we are going to follow up with ISS Tau, which is a mission of opportunity planned to be installed on the International Space Station by 2022, should it be selected in, I believe, 2019, because we submit the proposal. We have been down selected from the original proposal for phase A. We are completing the phase A. We have almost completed the phase A because we're writing the proposal to be submitted in May 2018, and we hope to be selected, or the selection to take place at least before the end of the year, in which case we would launch at 2022. So I'm not going to talk about all that. I'm going to go now into the proposed wide-field gravitational wave follow-up missions. So Transient Astrophysics Observer is our ISS Lobster or ISS Tau. It's a mission of opportunity. It's a $70 million of mission of opportunity, and it would work as what we call a pathfinder. We don't expect to find a huge amount of counterparts, but we will show that there are, although has shown, of course, with Fermi, but I hope that this will have opportunity to find more counterparts, electromagnetic counterparts. The Transient Astrophysics probe, it's a medium-sized mission. It's a probe, about $1 billion. It will be operational late 2020s, early 2030s, if it is selected. This is input to the upcoming decadal survey. And this is actually the industrial part in the field. It will hopefully collect a large number of counterparts for LIGO and LISA sources. Both missions emphasize time domain astrophysics. The ISS tau overview is that it will be a single lobster module on a pointing platform on the ISS with a 380 square degrees field of view and 1 arc-minute localization. It will also have gamma ray detectors. We're discussing now with our colleagues at the Israeli Space Agency at Technion. And basically, it could be 2 to 6 modules. We're still not completely settled. It has actually been proposed for several times. The first time we proposed with Neil at 2010, it was a free flyer and it wasn't selected. As an opportunity, it was canceled. The selection was canceled in 2012 because they ran out of money at NASA. 2014, it was declined because of uncertainty about LIGO and the results. Actually, the major weakness was, will there be triggers of gravitational waves to follow up? Well, now we know. And at 2016, we got a Phase A contract. The final mission selection, we hope, will be in December 2018. So there is a wide field imager. This is the lobster. And it has a field of view of 0.25 steradian, 1 arc-minute. The energy range is 0.3 to 6 keV. It has CCD detectors, and these are being built in MIT. And the optics is microchannel plates. Sensitivity is 10 to the minus 11 ergs per centimeter square per second in 2,000 seconds. And there's a gamma ray transient monitor, 25 kV to 1 MeV, based on Technion, Israel. So I guess I have 3 minutes now. Okay, so let me now go to, I just wanted to say that we can, depending on how many gravitational wave detectors are functional, are working, we can actually image the whole error box of a gravitational wave trigger, or we can tile it with 4 observations with tau. Okay, so I am going to go to the counterpart rate. The observation of the previous merger, of the first merger, I should say, significantly lowered the uncertainty of the neutron-star merger rate to 300 to 4,500, and that's significantly lower, per gigaparsec volume to the minus 3 per year. If you calculate the expected counterpart rate for ISS tau, taking into account the enhanced binary neutron-star merger rate of 440 megaparsec, which is based on the enhancement of the gravitational wave signal along the axis of the jet, plus the inclusion of the sub-threshold triggers into this rate, the beaming factor of 1/50 for the X-ray afterglows of the short gamma ray bursts, and the afterglow detection efficiency of 70%, as Swift has shown us. The counterpart rate detection rate is 1 to 20 events per year. Before GW 1708-17, it was 1 to 2 events per year. So the upper range increased significantly. So TAP now is the Transient Astrophysics Probe. It's one of 9 missions that have been funded. Have been funded by NASA for a probe class concept study, which will be input to the decadal survey. Currently, it's undergoing mission design and cost study, due 12 December 18, and if chosen, it could be launched between the end of 2020s and the beginning of 2030. So, what's on top? It comprises 3 wide-field telescopes, an X-ray telescope, a gamma-ray telescope, and an infrared telescope. And it's also designed to address electromagnetic counterparts to gravitational waves and time domain astrophysics. TAP telescopes have also lobster modules, this time 4, not 1, a field of view of 500 square degrees each, and a sensitivity of 10 to minus 11 in 2000 seconds. The telescope, infrared telescope, has field of view of 1 square degree. It has a sensitivity 23rd to 24th magnitude across the waveband for 500 seconds. An X-ray telescope, single crystal silicon mirror, 1 square degree, and 3 times 10 to the 15 ergs per centimeter square per second in 3,000 seconds. It's planned to be on L2 orbit, and it's planned to cost about $1 billion. And it would also address the same triggers from LIGO, advanced LIGO, and LISA at this point. So, and it will also be a time domain astrophysics observatory as well. I guess I'm about run out of time. I just wanted to say that NIL was indeed the powerhouse that glowed and lit our community. To quote the poet, he gave a lovely light. We will miss his wisdom, his presence, his smile, and his friendship. And we'll all meet again at the restaurant at the end of the universe. Thank you.
Time for a few questions.
Yes.
What would Tau or TAP have seen from the gravitational wave event from last year? Is it sense enough to see the X-rays when they switched on 9 days later?
That's a good question. I don't know the answer to that.
Okay.
Maybe you mentioned this and I missed it, but what would cause a supernova remnant to increase in brightness so dramatically on this kind of time scale?
Yes, that's exactly why we're so interested in putting Chandra on it again. I don't know. That is a question we've been asking. We did the calculation several times. It indeed increased. So we're thinking we now need to put the big guns on it. We have 5 targets. We put 1 on MAXI. The second will be on this source. But we don't want to do it at the same time because we don't have time to work at the same time in 2 papers. Or Nick doesn't. And so this is the next, our next target, yes.
Do you have an estimate of the age, the type?
No, I don't, actually. But I can give you more information from the catalog. Yeah, it's really very puzzling. That's why I pulled it out to show, as well as the solar analog, as well as the nearby star.
Is it clear why these 2 regions that you are looking at have more interesting objects than other parts of the galaxy?
No, it's not, because the reason that we selected these regions, the reason I selected these regions, I should say, since I'll take the blame, is that they have most of the objects we know are looking for in these regions, 40 and 30%. Obviously, if we confirmed that we find more of these objects, that would be a good selection, or it would also say that this is already a complete sample. Both ways is not a wasted effort. However, I'm much more interested to go in the areas where it's just a wild guess or a fishing expedition, if you wish, because I hope to find more stuff that we haven't seen and more interesting stuff and new stuff there. But that will be the second step of the survey. Yes?
When you're talking about survey with gravitational wave signals, and you say this is 3 detectors, you can survey the whole error box. And if it's 2 detectors, you can tile.
Yeah.
And then, do you mean not the whole, you tile not the whole box of the 4 tiles you give example?
Yeah.
So
basically, it depends what the error box we get is from LIGO. It depends. It's 380 square degrees, so it depends on the LIGO error box how many tau tiles we're going to have to use.
but that means you took a quite long time.
No, I mean, we can find a 2,000 seconds per tile. We can find a sensitive source there. I mean, we are sensitive to detect an X-ray afterglow there.
Thank you.
So back to Tzvi's question about the areas in the galaxy. I noticed it excludes the bulge, or the central part of the bulge. So could it be an observational effect that this is where we find more sources? I don't know, does the bulge provide some kind of background?
The reason that the bulge is excluded is because, first of all, it's much above the galactic plane. So it will need a different effort. I mean, we discussed this as well. And then there are some surveys already, if I remember correctly, and correct me if I'm wrong, Brad, there is a survey of the bulge as well that's going on right now with SWIFT. But we are very much aware that in order to have a homogeneous survey, if we get to the point where we're done with everything else, we should try to see if we can put together archival observations or at least observe the areas that don't have them to complete it. But this is far in the future. I mean, the main idea is to complete the plane of the galaxy first, and then the bulge.
The ongoing bulge survey is also very shallow.
Yes, like there is, I should say that there is another XRT survey of the galactic plane, of which I haven't really seen a lot of results yet, but it was 500 seconds, and it was very shallow. So I don't see. Maybe that's why we don't see a lot of the results yet. I don't know.
Well, if there are no further questions, let's thanks Chryssa again.
Thank you.